So hello everyone, this is Wilson Fandino. Because I'm seeing so many new names here, so let me just introduce myself. As I say, my name is Wilson Fandino. I'm one of the consultant anesthesiologists working here in London, in the UK. And I'm not a statistician, but I just wanted to share with you my own perspective of what I understand by biostatistics. And today the topic is going to be ANOVA and all the related variables. So I hope you can hear me well. Yes?
Yes, we are here very well, Wilson. Thank you.
As I said, this presentation is dedicated only to explore the topic of analysis of variance. And then let's go straight to the presentation. I'm going to share my screen. Okay, so I'm hoping I'm sharing here. Am I sharing?
Yes, we are seeing the Zoom. Yeah, now the PowerPoint one. Great.
Great. So let's start. So I'm hoping that it shouldn't take me more than, I don't know, it's hopefully no more than an hour and a half, but please feel free to interrupt me, ask questions. I'm going to try to do this as interactive as possible. So yeah, let's start now. So I would like to start my presentation with my concept map, only to put you in the right context. So as I explained to you last week, so we got here the classification of the variables, and depending on what your dependent variable is and what your independent variable is, we are going to come up with the right test. So so last week we were dedicated our week to study the chi-square, the J correlation, the feature exact test. I'm happy that by now you have a better idea of what it is. And then last week we were dedicated our meeting on Sunday to the concepts of normality, equality of variance, and when to use the ANOVA, when to use the parity test, when to use the repeat measures ANOVA. And it's important for you to understand that this there's always a non-parametric test. For the case of the t-test, we got the human win test. For the case of ANOVA, we got the Kruskal-Wallis test. For the case of pair t-test, we got Wilcoxon, and the repeat measures ANOVA, we got the Friedman. So today I will try to cover ANOVA with all the versions, including one-way ANOVA, two-way ANOVA, Factorial Anova, Ancova, multivariant ANOVA, repeat measures ANOVA, and there's a couple of tests, if I have time to discuss, which are the Kruskal-Wallis and the Friedman test. And then finally, we are going to dedicate some minutes to speak about the post-hoc analysis. This is a complex topic, the topic of post-hoc analysis. I'm hoping I have time, but if not, I'm always happy to take questions if you have. Okay, so okay, so I'm going to skip this. I'm going to start with a very short story that I hope you like it. This is going to take me about hopefully no more than 5 to 7 minutes. It's just to put you in the right context, in the context of generalized linear models. I have to tell you that before the 20th century, we had no idea. We were completely ignorant about statistical tests. And it wasn't until this gentleman, William Gossett, Karl Pearson, and Ronald Fisher, that the statistics actually evolved during the 20th century. And so, I mean, surprisingly, before 1910, no one knows about biostatistics, no one cared about that. And I consider this gentleman the fathers of the biostatistics, of the modern biostatistics. And I mean, a few of them describe the test that we know today before 1935, before 1940, before the Second World War. And many of the tests came up as well. Many of the tests were described after the Second World War, like in the 1940s, 1950s. But so is William Gossett. So as you can see, surprisingly, all these statisticians were born here in the UK. So he was born here in Canterbury, which is in the south coast of England. Karl Pearson was born here in London as well, and Ronald Fisher was born here in London, and they were all contemporary. But they were working completely independently. Actually, William Gossett wasn't a statistician at all. He was working in a beer factory, which is called a brewer. And I'm sure you've heard about the Guinness beer, which is an Irish one. And he was working there. So, he was actually dedicated most of his life to study the quality of the beers. And then if I asked you that he was comparing two types of beers, and the types of beers were based on the content of resins, and the resins is a continuous variable. So which test would you use to compare the two beers? I mean, if you got a container with a certain type of beer, and we've got another container with a certain type of another beer, and then you are kind of measuring the resins, and the resins are continuous variable. And then if I told you that those continuous variables follow a normal distribution, which test would you use? Does anyone know which test to use?
Flavia just answered in the chat t-test, also t-test.
T-test. So I can tell you that William Gossett was the one who invented the t-test, and we don't really know anything about him because he liked to be called the student, because he was the student of Karl Pearson, and then all his publications were named under the name of the student. So this is what we all know today by the t-test. The t-test was first described by a non-statistician guy, which was William Gossett in Ireland, and he was British non-statistician. He was working, as I said, in a beer factory. And then regarding Karl Pearson, as I say, he was the teacher of William Gossett. And so Karl Pearson, you probably have heard about him because he described the chi-square. He was the first to describe the chi-square, and also the correlation that we are talking. I think we will be talking this week or next week. The linear correlation was first described by Pearson, and then Ronald Fisher as you know, feature is the exact test of feature. He described the test by, I think it was like 1950s or 1940s. And this is what we know today as feature test. But he also described the analysis of variance as well. So you will see later on during the presentation that feature is important when we talk about analysis of variance, the ANOVA, okay? So why am I telling you this story? Let me just escape a little bit from here, and then I'm going to go to my STATA. So why am I telling you this story? I'm going to do very quickly a t-test. Just bear with me only 1 second, please. So as I explained to you, I'm going to rename my variables here. My variable 1 is going to be group, and my variable 2 is going to be, for example, mean blood pressure. And then let me just double check here to see what the STATA did for me. So we got 2 groups. 20 participants, 10 in each group, and we got, for example, a mean blood pressure, and which is a continuous variable. So provided that normality or sensitivity, I can run a t-test. So t-test dependent variable. Always don't forget the comma and then by the group. I also explained to you that ANOVA, we can run ANOVA with 2 variables. So let's do this. ANOVA, always your dependent variable first. And there's another way to do ANOVA, which is one way. And then one way dependent variable and dependent variable. Dependent variable. Okay. Here. Sorry, it will take me less than a minute, okay? Sorry, it's a little bit slow. I'm almost there. I'm going to create a new Word format. This is something that I already explained to you last week. Tools. Okay. Okay, so let me just explain to you a little bit. So what I did here was, again, I'm going to repeat this. So I've got 20 patients or 20 participants, 10 patients in the group 1, 10 patients in the group 2, and I'm trying to compare the mean blood pressure among or between the groups. So if I run a t-test, I already explained to you that the number you should look at is the 0.6323. But then if I run the ANOVA, this is going to be, it needs to be exactly the same as you can see here, as I can demonstrate here. And then for the one-way ANOVA, it should be exactly the 0.6323. And then for, this is the command for linear regression, by the way. And then as you can see here, is exactly the same p-value, exactly the same p-value, which is, in this case, obviously is not significant. But my point is that all these tests, which were independently invented by these guys, by William Gossett for t-tests, correlation by Carl Pearson, and ANOVA by Ronald Fisher. So they are actually not quite different each other. Actually, you shouldn't look at them completely unrelated because they are related. And actually those tests, the t-test, the linear correlation, and the ANOVA are called generalized linear models because they are from the same family. And as I can demonstrate you here, the t-test is just a way to do this, but you've got another way to do this, which is ANOVA, which needs to be exactly the same because I'm dealing with the same data. And then the regression, if you run a regression model, it should be exactly the same. So please, my message to you is don't look at the test completely independent because they are all very often related. So that's my point before starting talking about ANOVA. Okay. So the next question I would like to ask to you is what exactly is ANOVA? What do you understand by ANOVA? I mean, if someone asks you what do you mean by ANOVA, what would be your answer? I just want to see in the chat your the definition of ANOVA in your own words. Okay, I can see the chat here. Yes. So Sophia said it's a parametric test that can compare more than two groups, which is correct. And so ANOVA is the analysis of the variance. It's a way that we use to compare the dispersion, the dispersion of the data to see where our data are different or not. But what exactly is the variance? So this is something that you should keep in mind as well, because these concepts are completely related, and you should just, I mean, it's very difficult to have the statistical concepts in your brain completely unrelated. You have to relate all these concepts in order to consolidate your knowledge, because otherwise it's going to be very difficult to understand this, okay? So this is the definition of the variance. This is just a mathematical equation, and this is the standard deviation. I did explain to you that the standard deviation is no more than the square root of the value of the variance. And then this is the standard error of the mean, and the standard error of the mean is very important to understand in order to interpret the t-test output. And this is not more than the standard deviation, which is the S, divided by the square root of the N, when N is the total sample size of the three groups or whatever the groups are. So as you can see here, we got 10 patients or 10 subjects represented by my green points here and here and here. And then for these 10 patients, I calculated the mean or the average, which is quite easy. And then the variance or the standard deviation is just a measure of the dispersion of this particular value to the mean of the group. Okay, so you can see here, for example, this patient or this subject is a little bit far, or maybe this one is quite far from the mean, is quite dispersed. And for example, for this value is actually closer to the mean. So all you need to do is just take this value and then whatever this value is minus the mean, which is here, and then you just need to square this and then divide for the sample size, for the total sample size of this, or the sample size of your group, and then you will have your variance. This is the variance. So it's not really. I mean, if you see the mathematical equation, you probably don't understand, but hopefully you will better understand with these graphs. All right, so so same for the standard deviation. They are just two different ways to describe the dispersion of our data, provided that the data are normally distributed, because obviously they are not normally distributed. We are going to use interquartile range and basically that.
May I add a comment regarding?
Sure, Karla.
Regarding the concept of ANOVA, I was reading also, and I always thought, oh, we are comparing the variance, we are testing the variance, but in fact, ANOVA uses the variance to calculate, but we are comparing means, correct, Wilson? Because it can be a little bit confusing, because when we reflect about what the tests are testing, what the statistical test is helping us, it's important to understand our null hypothesis. The hypothesis we are testing. So the hypothesis we are testing is that these three groups has equal means. There is no difference. And
exactly.
Our alternative hypothesis is that this, at least one group has different means. So in fact, ANOVA will test means, but as Wilson explained very well, they will use the variance in the mathematical way to prove this mean difference.
Yes, and I think that's why I explained to you that all these concepts are related, and then this is because I mean the t-test compares directly the means, and with the ANOVA test you can compare the variances, but as I say, they are related, and they are three ways to do exactly the same thing. And because we are talking about ANOVA today, so we are going to talk about variances. But if we were talking about t-test, we are going to talk about means. But it's exactly the same. Well, it's not exactly the same because it's, the mathematical calculation is different. But there are two different approaches to solve out the same problem. So yeah, you're right, because we are not trying to compare. I mean, we're just trying to compare. Remember the null hypothesis, always remember the null hypothesis. And the null hypothesis is that there is no difference between the two or three groups. This is the null hypothesis for the t-test, the null hypothesis for the ANOVA, and the null hypothesis for the linear regression. So, so this is exactly the same research question, whether or not this is different. These groups are different, but different approaches. How you can understand this?
Yes, thank you so much, Wilson.
Great. So, so having said that, this is again, this is the concept of variance. So I'm going to explain to you a little bit in depth this. We got three groups here, and treatment A, treatment B, and treatment C, and we got 20 subjects or 20 participants here, and you can see here, provided that they are, in this case, the values are meant to be the VAS scores. For example, 10 is the worst pain ever, and for example, here, 1 is the patient has minimal pain. And just trying to compare whether or not for this treatment is different, the VAS score for this one and for this one. So it's exactly the same. So you just need to, because the mean for the treatment A is 6.85, the mean for the treatment B is 6.90, and the mean for the treatment C is 3.75. So you just need to take this 9 minus the mean for the group, and then you just need to square, and then continue with this, continue, and then you will come up with a number here, and then just need to divide this by the number of, or the sample size of the group -1, which is, I did tell you that there were 20 patients here, so it is going to be 19. And this is going to be the sum of the squares here. Sorry, the variance. The variance is going to be here. The variance for the group 1, the variance for the group 2, and the variance for the group 3. It's not, I mean, you see in this way, it's not really difficult to understand the variance. So my null hypothesis in this example is where the 4.56 variance of the group 1 is different from these ones, or if there is a difference at all in the treatment. And obviously, I mean, you might already predict that this group C is different from the group B and the group A, and you can see here, because, you know, I made it in purpose that this group had less pain. And you can see there is a 2 here, there is a 2 here, there is a 1 here, and then here there is a 10, there is a 10 here, yeah? So, I'm really hoping that this group is different from the group A and the group B, but I need to prove this. And the way to prove this today is with analysis of variance. So this is something that I found last night. This is a prospective study looking at the impact of creatinine clearance in clinical outcomes in people with atrial fibrillation receiving apixaban. And I thought it might be a good idea to work with this. However, it was just published last month, and it was a prospective study, but for the purpose of teaching, I'm going to assume that this is going to be a clinical trial. And then I'm going to, for those who maybe don't remember or don't know, apixaban is anticoagulants that we usually give for people with atrial fibrillation, but also people having deep venous thrombosis, or in the postoperative context of having a hip replacement in order to prevent the coagulation and the embolic problems in these populations. So this is just one of the anticoagulants for that family, but there are also
eu tenho uma listinha de coisas para comprar, mas para comprar aí. Fez dodói.
Please, everyone. Please mute your mic, please.
20 pessoas no voo.
Yes, I think there is some noise in the background. I don't know where is it coming from. Yeah, great. So I was mentioning that apixaban is an anticoagulant, but this is not the only one. We got rivaroxaban, which is from the same family, and the other one is called edoxaban. So I think I'm going to use this idea for my examples. Okay, good. Right. Now I'm going to create data set here, and let me just clear this. And then, because we are going to talk about 3 groups, I'm going to create 3 groups here. Three groups here, as you can see. And then I'm going to generate my my continuous variable, which is going to be the clearance of creatinine. Let me just okay. So I just made up this data set. Hopefully you can understand this. So I'm just trying to, let me just finish with this, and then I will explain to you what are we doing today, okay? Great. So I'm just going to rename my variables. This is another way to rename the variables, by the way, because I did teach you last time a way to rename the variables, but when you have multiple variables, maybe, I don't know, 10 to 20 variables, is time consuming, so you can actually rename the variable, sorry, rename here by saying instead that which are the all variables, which are in this case variable 1, variable 2, and variable 3. And then in this case, I'm going to say that the new name for the first variable is going to be group. The new name for the second variable is going to be the creatinine clearance. Just following the example I just mentioned to you, and the last one is going to be age. Okay, so hopefully STATA just generated for me a new name. So hopefully it makes sense. So we got 3 groups, 10 patients in each group. And then we got the creatinine clearance for each patient, and then we got the age of each patient. And just imagine that those 30 patients are having atrial fibrillation, and then we are just trying to compare the group 1, which would be, for example, let's say, let's close this, just to make a little bit of sense. Group 1 is going to be, for example, rivaroxaban, and the group B, rivaroxaban, and then the group B would be, for example, sorry, the group 2 would be apixaban, and the group 3 would be, obviously, I mean, you can, sorry, this is apixaban, and then the group 3, it would be, for example, edoxaban. Okay, so hopefully everyone can understand my my research question. So my next question for you would be, for example, if I'm trying to compare the creatinine clearance among these groups, hopefully you will, by this time, you will be able to say that the right test to use is Anova, provided that obviously they are normality, homozygous zero variances, and the data came randomly. But I've just add a third variable, which is the age. So if my outcome variable was still the creatinine clearance, and I was, if I was comparing the creatinine clearance between groups, but then there is another variable which is a dependent variable, and is age. So if I was going to compare the three groups, and the outcome is creatinine clearance, which is a continuous variable, and age is a dependent variable, so which tests would you use, provided that there's normality of data and homoelasticity, equality of variances? So Gisela say linear regression, Flavia say linear regression, Chris Tavares, two-way Anova. Any more thoughts? Sofia and Capies say Anova, Carlos say Ancova, Alejandra, Annabella, Voto say Anova, and Ahmed, yes, the data is normally distributed, Livia, Ancova. Yes, okay, great. So this is the introduction, and for my first test, which is called analysis of covariance, is the Ancova is the right answer. So well done, Karla, and I don't know who else.
Livia also answered.
Lydia, yeah. So this is the example for Ancova. Hopefully you can understand this. So the analysis of covariance is like a combination between the analysis of variance, which is the group and the creatinine clearance, and the linear regression, which is creatinine clearance and age. Why linear regression? Because we are comparing creatinine clearance with age as well. Yeah. So because we can include these variables in the same model, so we can use Ancova. And then I just wanted to start with this because it's important. When I was a student, I really had trouble to understand this. And as I say, it's very easy to understand now because Ancova is just the same Anova, but with a continuous variable as a dependent variable in addition to the group, which is a categorical variable. So how do you run this test? So I'm going to run. Let me just think a little bit. Yeah. So so hopefully by now you can understand the story I start with in this presentation, that when I explained to you that Pearson discovered, or Pearson described the linear regression, Fisher described the Anova, but all these terms are related. Are related. So this is the beauty of biostatistics, because as I say, and I can't emphasize enough that you shouldn't see these tests as separate ones, because it's going to be really difficult to memorize this. But if you try to correlate those ones to relate each other, is much easier. And this is just an example that you can combine two generalized linear models, which are Anova and linear regression, to construct your model. Yeah.
Wilson, one doubt that we just discussed on
the chat.
I'm sorry, are you hearing me? Sorry.
Yes, I can hear you.
Regarding this example, is it an option to use linear regression? I guess no, because we have three groups, right? I think it's not possible to use the simple linear regression in this case. That's the why we must use Ancova.
Yes, yes, you're right. But remember that all these states are related. All these states are related. This is the linear generalized model. So I can emphasize enough. This is exactly the same problem with a different perspective. So in this example, you can't actually run linear regression because we got 3 variables, but you can run a multivariate linear regression, which is another way just.
It was my second question, because we could use, if we use a multilinear regression model.
Yes, yes.
But Ancova is a kind of multilinear regression.
It's kind of, but it's a combination. That's why analysis of covariance, and the covariance. In my example, the H is called the covariable, which is the continuous variable. But I mean, the definition of the analysis of covariance is a kind of mixture between the analysis of variance and the linear regression, and I explained to you why. Okay, so how did you, in this example?
Sobha asked a great question also in chat.
Yes.
Is the group, a group is a variable, a categorical variable. Creatinine is the dependent variable, and age is a covariate. I guess yes.
Which is dependent variable as well.
Yeah, yeah.
Yes. Exactly, yes, exactly. You are right, Shobha. Actually, you can, as I say, you can ask me questions because I'm just trying to make this as interactive as possible. So please don't be afraid of interrupt me and ask me questions, okay? Great. So I was saying that if I've got this data, I'm going to run Ancova. So the way to run an Ancova is just Anova. And then you just need to type the dependent variable. So which one is your dependent variable is creatinine clearance. And then your independent variable is going to be the group. And then here you just need to tell Anova, look, my next variable is going to be continuous. So that's why I'm typing here C dot for continuous. So Anova can say, oh, this is a continuous, right? So I'm going to say, yes, H is going to be my continuous variable in my model, okay? So I'm going to say here, Anova creatinine clearance group. So this is just one way Anova if I type like this. But if I add this to my command, so immediately it becomes an analysis of covariance, right? So you can see here that, by the way, the p-value you should look at is the f value. And do you actually know why is it called f value? Why is it called the f test here? Have you ever wondered why? Let me see the chats.
Yes, Wilson, Amhed and Sophia made some comments. I guess it's great to reflect with them.
So does anyone know why is it called F test?
I know that it's as the t value,
yes,
Anova has f value, and f value will help us to find the p-value that it represents in the end.
Yes.
I'm sorry, I don't know from where this f value comes, but I know that, for example, if we are doing by hand the Anova,
yes.
we would need this table of f value to find our p-value.
Yes, exactly, Karla. But my question was, why is it called? Because I think it's important as well, rather than memorizing this. So try to make sense of this. Why this is called F and not, I don't know, it could be called anything. But what is the F? What does it stand for?
Yeah, feature maybe.
Yes, exactly. So it's F for feature, because as I explained to you in my story, feature described the Anova test. So this is why he said, I'm going to call this F test. So it's F for feature, okay? Right, so this is the Ancova. Hopefully you will have a better idea of what Ancova is. And then my next step is I'm going to teach you how to, well, I can see 33 participants now, so we got great participation today. So I was going to say, my next exercise, I'm going to teach you how to dichotomize the variable. Did you know?
Wilson, just to clarify on the chat, had asked if in this case you are comparing one independent variable, the group of medications, with two dependent variables. I guess exactly these we are comparing, right?
Yes. So.
And we need Ancova in this situation because we have three different groups.
Yes, exactly. Yes. So just remember this. Remember your model. Your model is always starting, and this is useful for ANOVA models. This is useful for linear regression models and for logistic regression models, for everything. So your model should start with your outcome, which is your equation, and then your outcome should be equal to the dependent variable. I'm going to call this dep1 plus dep2 plus dep x, which means that whichever or how, it doesn't matter how many variables do you have in your model. And so according to my model, the outcome variable is going to be the dependent variable. It depends on your research question, but as I explained to you with this article that I found last night, so my dependent variable is going to be the clearance of creatinine, and then my dependent variables are going to be the group, because I would like to see whether or not the group is the clearance of creatinine is different among groups. But then I'm going to add a second dependent variable, which is called the age. Why am I doing this? Because I will be interested in knowing whether or not the means among groups are different but adjusted, and this is the key word, adjusted by the age, which is the beauty of Anova. So, because as you might understand, the age is, it might be a confounder for the creatinine clearance. So I would like to see where adjusted by age, this creatinine clearance is different among groups. And this is what my model is trying to say to me. Regarding the outputs, I'm going to explain to you in detail, maybe in 10 minutes time, I'm going to explain to you in detail what each number of these means, okay? Did it answer your question?
I'm not sure. I guess students, please, it was clear, students, to you all regarding this other variable, dependent variable that we add in the statistical test. I guess it's important because we know that age will influence. So if we exclude age in this equation, we could have a wrong result. So that's why age is so important, and we must find a test that add this important aspect in consideration, right, Wilson?
Yes, it is important, but again, it depends on your research question, because I'm suspecting that the age is related to the creatinine clearance, and I might be right. But if your research question doesn't have anything to do with age, so as I say, I mean, you can run this, And obviously the p-value is going to be totally different here. And this is just going to be one-way Anova, creatinine clearance and group. And then the other one is the Ancova, which is adjusted by the age. So if you suspect that the age is a confounding variable that might confound the creatinine clearance, you must include the age.
Excuse me, Wilson, I'm sorry to interrupt, but there's a lot of doubt about what is the dependent variable and the independent variable. If you can
Sure.
make very clear, because there's a lot of dates in the chat. Sorry to interrupt you.
Yeah, that's the idea. That's the idea. So the idea is that everyone can understand this. So the outcome in this case, okay, the outcome is going to be the creatinine clearance because of my example. The outcome could be the age or whatever the continuous variable is. I mean, you just need to include here a continuous variable, but I'm just talking about my example. This is something that I would like to point out. This is just my example, right? So in my example, because as I show you, the impact of creatinine clearance on clinical outcomes in elderly age of relation patients receiving apixaban. This is what I'm just trying to explain to you. If that is your research question, so your dependent variable is going to be the clearance of creatinine, and this is going to be equal to your dependent variable is going to be, the group is always dependent, and the syntaxis is always, sorry, excuse me, the group is always independent, and the syntaxis is always dependent, independent, always, okay? I mean, there are a few exceptions to the rule, as you will see when we are talking about repeat measures Anova, but generally speaking, this is true, okay? So in my example, in my particular example, my outcome variable, which is the response variable, or my dependent variable is creatinine clearance, and my independent variable or explanatory variable, you can call it either way, is going to be group, and for my model, is going to be age as well. So according to my model, what I'm trying to find out is where the means of creatinine clearance among groups are different adjusted by the age of the participants. Is it more clear for you now?
It is more clear, yeah.
More clear. Thank you, Gisela. Good. So let me just talk about the dichotomization of the variables, because I believe it's important as well to understand this. Let me just minimize here. Right. So let's go back to, sorry, I've got some problems here with the screen. Yeah. So let's go back to this case. Right. Yeah. And so in order to categorize your variable or dichotomize your variable, you just need to type, just need to generate a new variable, gen for generate, remember. And then I'm going to generate that variable, which is called, for example, age categorical, age cat. And this is, I mean, you can name your variable whatever you want, yeah? But my new variable is going to be age categorical, age cat, which is short for age categorical. And then this new variable, I'm going to say STATA, that this new variable is going to be the same as age. I'm going to explain to you why, okay? So, and you can see here hopefully STATA has just generated a new variable here, which is called a categorical, exactly with the same numbers of the age. As you can see, is this variable is identical. Yeah. So one way to do this, and I did explain to you this a week before, is to replace the command replace. So let's see, replace what? Replace age cat equals to 1 if the age is less than, shall we say 40? If the age is less than 40. And then I'm going to run the same command, replace age cat equal to 2 if the age is more or equal to 40 and age again is greater than 60. And then I'm going to repeat the process, replace age cat equal to 3 in this case. If the age is, let me think, is more than 60. And age is more than 60.
Sorry, it shouldn't be less than 60 in the previous one.
Yeah, sorry. Yeah. Thank you for this. Let me just, sorry, I need to start again. Sorry about this. So I'm going to drop this age cat again. I'm going to drop this variable and then I'm going to generate again. Sorry about this. Generate again age cat equal to age. Let's see what STATA did for me. Yeah. And then I'm going to replace again. Replace age cat equal to 1 if age is minus than 40. And then replace age cat equal to 2 if age is more or equal than 40 and age is less than 60. Less than 60, right? And then replace age cat equal to 3 if the age is more or equal than 60, right? Hopefully you can understand this. Let me see. Yeah, good. So what I've done here is just categorize my variables. So I've got a new variable here, which is called age cat, for short for age categorical. And because of my rule, this patient, which is 23, is going to be categorical 1, because I say that everyone who is less than 40 is going to be 1. And then because this patient is between 40 and 60 is going to be 2, and then so on, okay? So this is the way to categorize your variables. Yeah. And then there is another way to do this, which might be slightly more complicated, but I'm going to show you because you're dealing with big data set that is more efficient. So again, I'm going to generate, let's say, a new variable which is going to be age cat 1. I can see I can say age cat because age cat is already generated. So let's generate another one, which is called this. And this is going to be equal to the age again. And then hopefully this data is going to understand what I'm trying to do. So again, I've just generated a new variable, which is exactly the same as the age. And then the other way to do this is with the command record, which is, I believe is more efficient. So record what? I'm going to record my hcat1, and then I'm going to say that the minimum to 40 equal to 1. Then another parenthesis to 41 to 60. Sorry, 41 to 60 equal to 2. And then 60 slash max equal to 3. All right, so minimum 41 to 60 equal to 2, and 60 to max to 60, maybe this is going to be 61.
Yeah, 61, yeah.
61 to max, okay. Great, so as you can see here, this is my new variable, which should look exactly the same as the hcat, and this is just, I just made this to explain to you that there are two ways to categorize your variable, and as I said, the syntaxes of this might be slightly more complicated, but it's not really hard to understand, and it's more efficient because you can do, I mean, you can do many variables at the same time, and the disadvantage of replace is that you have to do every single variable by hand, so which is not efficient when you are dealing with a big data set. Is it clear?
Yes, Wilson, thank you so much.
Perfect. So great. So the next one I'm going to talk to you about is let's start again with the Way Anova.
Wilson, students, yes, they are asking why we are categorizing. If you are planning to run, okay, when we categorize, it's because our research question is different from using only continuous variable. But when we categorize, we will use a different statistical approach for this.
Yes. This is just to show you how to categorize variables because I believe it's important. But the second reason is because we are talking about Anova, and we are doing Anova. We have to categorize the variable because if we don't categorize the variable, I'm still working with Ancova. The third reason I'm doing this is because in many instances you got the age in your data set as it comes. 21, 32, but again, it depends on your research question, but sometimes it doesn't make any sense to include in your model the age as a continuous variable. And I'm going to explain to you why, because if you run a regression model and then you include the age variable as a continuous variable, that's okay. I mean, there's nothing wrong on this, but just remember that in your output, your understanding that the beta value is for every year, which might, I mean, if that is significant, that would be statistically significant, but that wouldn't be clinically relevant. So you have to understand the difference between significance from the statistical point of view and clinical relevance. If I'm constructing a model and I say to you, for every year, the beta value is going to be, I don't know, like 1%, so it doesn't make any interpretation to me in the clinical context. It depends on your, it always depends on your research question, but yeah, I mean, I just wanted to show you how to categorize the variables because I think it's the right time to speak about this because we are talking about Anova.
Okay, thank you. And Livia is asking if we will use only categorical variables as independent, we can use two-way Anova?
Yes, exactly. That's the reason I categorize my variable, because my next topic is going to be two-way Anova.
Great, thank you, Wilson.
Okay, great. So back to my data set. I don't really need this HCAT one. I just wanted to show you how to do this, but I'm just going to drop this variable just to avoid any confusion. And then this is my data set. Yeah, right. So if you were planning to do a one-way ANOVA, because we haven't talked about one-way ANOVA yet, and then I will try to explain to you what we mean by one-way ANOVA. So with one-way ANOVA, I'm just going to compare this creatinine clearance with the group, okay? I did explain to you how to do this. So ANOVA, so dependent variable, which one is the dependent variable? Is going to be creatinine clearance. And then the dependent variable is going to be the group. Okay, this is the simplest version of your ANOVA. And I just wanted to introduce you to the output of ANOVA, okay? So what you can see here is the number of observations, obviously. I've got 30 patients, so this is the sample size, and then the root of the mean square error. I have to tell you, I forgot to tell you something important, that when we are talking about ANOVA, we are just trying to split the total variance. So the total variance, and I did explain to you the other day, but I'm going to explain to you again because I believe this is important. The total variance is equal to the between group variance plus the within group variance. This is what we are trying to do. Is it clear for everyone what the within group variance is and what the between group variance is, what the total variance is, how to calculate this? Let's see the chat.
Wilson, I guess not really. Maybe some students understand the concept behind, but exactly how it works, I guess you could try to clarify for us.
Great. So let me just stop a little bit my STATA and let me go back to my presentation, and then it's actually my next slide. So this is one-way ANOVA, and let's imagine that if you got 80 patients here. This is not the same example because in my example they were 30 patients, but just imagine for a second that we got 80 patients here, and every diamond here is represented by one participant, and you got the total sample size here, which is clear for everyone. So obviously, because this is a clinical trial, so I have randomized these patients, and then I have allocated, because there are 80 patients, there are 60, there are 5 groups. Let's imagine that the group 1 is rivaroxaban, the group 2 is apixaban, the group 3 is edoxaban, the group 4 is warfarin, and the group 5 is placebo, for example. Yeah, so so you got 5 groups here, and then I have just randomized these patients, and because of the randomization, I got 16 patients in each group. And then, so what is the total variance? If you put these patients together, the whole patients together, and then you calculate the variance that I did explain to you here, yeah? So you just need to calculate not for the 20 here, but for the whole 60 patients, the variance, and then you will come up with a number. And this is the total variance of the group, regardless the allocation of the group or the other factors that might have the model, right? So I think the total variance is easy to understand. And then what is the between group variance? Let's talk about the within group variance first. So if I am telling you that I've got 5 groups, and then each group has got 16 patients, 16 times 5 equals 18. So I'm actually able to calculate the variance for this group, and the variance for this group, and the variance for this group, and so on, in the same way that I calculate the total variance. So this is the within group variance. Within group variance, this is the way to calculate the variance, okay? And then because the within group variance is straightforward and the total variance is straightforward, but then what is the between group variance? So I'm going to explain to you what is the between group variance. So hopefully you will understand what the within group variance and the total variance is. And then if I go back here, so I just say that the total variance is the between group variance plus the within group variance. I did explain to you the total variance, what the total variance is, and I also explained to you what the within group variance is. What is the between group variance? So it's according to my equation. So the between group variance is equal to what? To the total variance minus the within group variance. So you see here, I mean, this is simple. If I'm telling you that the total variance is equal to the between group variance and the within group variance, you know what the within group variance, you know how to calculate the within group variance, you know how to calculate the total variance, but the big question is how to calculate the between group variance, which is the one we are interested, because the between group variance is going to tell us where the groups are different or not. So how to calculate the between group variance? So is equal to the total variance, obviously, minus, because the within group variance is going to be on the other side of the equation, the within group variance. Is that more clear to you now?
So, Wilson, sorry for interrupt you. So within group variance will be the variance of each subgroup of the total variance.
Yes.
Am I right?
Exactly.
Okay.
Yes, that's what I mean. Okay.
Okay, perfect.
Great. Okay, so let's go back to my example here, because I was trying to explain to you what this means. I was saying that this is the sample size and this is the root of the mean square error. This is a little bit confusing because there's, unfortunately, in statistics, there are many ways to name exactly the same thing. So in this case, this is going to be the variance of my group, the between group variance, okay? This is going to be the within group variance, and this is going to be my residual variance. Sorry. I don't know if I said the other way. This is going to be the within group variance. This is going to be the between group variance, and this is going to be the total variance. Sorry for the confusion. Maybe you understand better this by typing one way. One way dependent and the independent. As I said to you, it's exactly the same output. It should be exactly 0.8835 and 0.8835. But then this is what I'm trying to explain to you. So the between groups and within groups here, right? You see this? So it's exactly the same interpretation for the interpretation for the one way is exactly the same for the ANOVA. So back to my example. So the root of the mean square error is going to be 20.1888. So this is exactly this number, as you can see here. Yes, this number, which is 407.58. If you take the root square of this number, I'm going to calculate the root square. So this is going to be display, and then let me just, this is the root square. So the root square of 407.58 is 20.18, which is exactly this number. You see this? It's exactly the same one. So it's the root square of this number. This is what Anova is calculating for us. So, so the next item is the R square, and the R square is how well my variables explain the model. In this example, it's a pretty bad model as expected, because I'm not obviously that was really a random sample, so I'm not really expecting any difference. As you can see here, there is no difference here in between groups. So the R square is the interpretation of your model. So because it's 0.0091, so that actually means that the 0.91% of the model is explained by my variables, which is absolutely useless, my model, as I say, because I'm just trying to explain to you the output of this data. But this is something that you have to make it clear, because this is not a p-value. This is just an expression of the, if you multiply by 100, it will be an expression in percentage of your model. So because I'm multiplying here by 100, I would say that 0.91% of the model are explained by my variables here, by my variable here, because there's only one variable, which is the variable, the group variable. And then the adjust R square, this is the one you should look at, because sometimes when you are dealing with big data and you are oversaturating your model with too many variables in your, too many independent variables. So there is a problem with this, because you might be adding some variables that they are not useful for your model. So this is what the adjust R square means. So the main message I would like to leave to you is that when you see an output of Anova, you should look at the adjust R square. And you can see here that it's actually even worse, the explanation of my model, because this is just an example. And then this is the partial.
Yes. Sorry for interrupting you also, but just to explain and highlight this. For example, even with a p-value, statistically significant p-value, we may have a model that really doesn't work, right? Or not, or this value are related, because this R square value, it's important to understand if our model, if the correlation, the interaction between the groups and drugs and our outcome really worked. In our example, it doesn't.
Yes, I think this is a great question, Karla, and which I've never thought about this, but I would expect that if the R square is very low, as in this case, that would be correlated with non-significant value. I would be surprised if not. I mean, we could try with a different model to see, to make the groups statistically significant, to see what happens with it. That would be interesting, but
Okay.
I'm not going to do this, but because it's going to be, it's going to take me a few more minutes, but
okay. Thank you. So in general, with a great p-value, we will see a model that works in R-square values in general.
I think so. I mean, I would be surprised if not, because I mean, if your R-square is very low, which means that you're not really explaining your model with your variables. So I would be surprised if the p-value is significant, really. Having said that, the calculation of the adjusted R-square has nothing to do with the p-value. I mean, the calculation is completely different, but I would expect that they are correlated. So the next output I would like to explain to you is this one, which is my model, and because I've got only one variable, which is group. This is why it's called Way Anova, because only there is one variable, and because of this, the f value is going to be exactly the same. But this is not always. This is not the case for the two-way ANOVA, and I usually say that the p-value to look at is this one, which is the p-value for your model. Okay, and this is just the calculation of the partial sum of squares that I explained to you in my slide here. So this is just the calculation of these sums here without the denominator. You see here you just need to take this individual value minus, for example, I'm not going to spend more time in this, but the sum of the squares are the numerator on my equation of the variance, and this is what the output is going to tell me here. And then you have to divide this by the degrees of freedom. I explained to you the other day the degrees of freedom, which are based. Actually, I need to explain to you this again, because I think it's important. And someone was going to ask something.
Yeah, sorry. In this example of this slide, if these three drugs has a p that is significant, what can I assume? For example, in this case, it's obvious that drug A and C is different, because ANOVA, I can do a sub-analysis, but if it's positive, the biggest and the smallest, I can assume that they are different, statistically different, in this case, for example.
Great question, Paulo. Thank you very much for this. So yes, exactly. So I think if you look at my data, 2.93 is definitely different from 4.56. But then my next question would be, is it different? Well, obviously significantly different from 3.57? Because again, it depends on your research question and it depends on your data set, but you might wonder yourself, well, this is clearly different from 4.56 and 2.93. But is it relevant for you to know where this value is significantly different from the treatment B? It depends on your research question, it depends on your data set. But technically speaking, I think you should anyway run a post-hoc analysis. Because your reviewers are going to question why didn't you run a post-hoc analysis?
Between so A and B and B and C is not clear, but between A and C, if it's positive, its P is less than 0.05, it's clear different, right? In this case?
Yes, Paulo. So the topic, I don't know if I will have time to discuss the post-hoc analysis, because there are so many tests and they actually depend on your research question. They depend on whether you are interested in pairwise comparison. For example, if you are interested in comparing the treatment E with the treatment B, the treatment A with the treatment C, and the treatment B with the treatment C. If that makes sense for your data set, if that makes sense for your research question, you have to go for a specific test. But for example, if you are just interested in this and this, you can do this in the post hoc analysis. Or there are more complex calculations, for example, where the mean between the V, the grand mean between the V and C is different from the mean of treatment A. Or you might wonder if the mean of treatment A plus B is different from treatment C. So it depends on your data set. It depends on what you want to know.
Okay, thank you.
The post hoc analysis are very interesting, but they are complex. They are complex because there are at least 6 or 7 tests, and then you have to choose the right test depending on your what exactly you want to know.
Okay.
Right. So this is the.
Students also asked about if there is a value for R squared that it's acceptable to your model. There is a value. I can't remember if there is, but I guess Professor Fragni sometimes explained it.
It's very subjective. There is no literature about this. We usually, by the way, this R square is very related to the Pearson. And I mean, I can emphasize now that this is all related to everything. And for example, let me just make a very short parenthesis, because the R square is the one used in Anova. But then the R is used in the correlation, in linear correlation, right? So they are related because this is exactly the square root of the R for linear correlation. That's why I wanted to tell you my story in the beginning of my presentation, because all these terms are related. You have to consider the t-test, the ANOVA test, and the linear correlation related, because they are all from the same family, which is called linear generalized models. Regarding your question, so in this case, it's 6.43. I did say this is a completely useless model. Some people like to say that more than 80% is a good number, and between 60 and 80% is an acceptable number, and less than 60% is definitely useless model. It depends on where you read this, but I think this is generally speaking, this is the rule. Less than 60, useless. 60 to 80, acceptable. More than 80 is a very good model. And this is it applies for ANOVA, it applies for linear regression, and it applies for logistic regression. Right.
Thank you so much, Wilson. Thank you.
I'm going to explain to you, I know I did explain to you the degrees of freedom the other day, but because we got more students here, I'm going to explain to you with my slides, which is here. So the degrees of freedom, it depends on what you are talking about. If you are talking about the one-way ANOVA, which is my current example, or two-way ANOVA or factorial ANOVA. But for everything, the total variance, the degrees of freedom for the total variance is going to be n-1. And I'm going to explain to you only the one-way ANOVA, because otherwise it's going to take me a long time. But in this particular case of one-way ANOVA, which is the one we are running at the moment in mice data, So the between group variance is going to be equal k minus 1, where k is the number of groups, okay? Because I've got 3 groups, so I'm expecting that the between group variance here is going to be 2, because it's 3 minus 2, okay? Sorry, 3 minus 1, number of groups minus 1. And then the total variance is going to be n minus 1. Let me see here. So the total variance is going to be here, the degrees of freedom, because I've got 30 patients, so the degrees of freedom, I did say this, the sample size minus 1, so 30 minus 1 is 29. And then the within group variance is slightly more complicated, but you will understand by this. Let me just maximize this. So because I say to you that the within group variance is equal to the total variance minus the between group variance, and number 2, I say that the degrees of freedom is going to be n minus 1 and k minus 1 in this case of between group variance. So therefore, the degrees of freedom for the within group variance is going to be this one minus this one. So this is what I'm trying to represent here. N minus 1 minus k minus 1. And then you solve out the equation. So you will come up with n minus 1 minus k, and minus times minus equals to plus. So it's going to be n minus 1 minus k plus 1. And then this plus 1 is going to be eliminated by this minus 1. So finally, my degrees of freedom for the within group variance is going to be n minus k, 8 minus k. So back to my example, back to my example, n minus k is going to be n minus k. So what is n? N is 30, and what is k? K is the number of groups. The number of groups in my example is 3 groups. So 30 minus 3 equals to 27. Okay, so this is all only for one-way ANOVA. As I said, there are other ways to calculate this for the two-way ANOVA and for the factorial ANOVA, but I'm not going to talk about this because otherwise it's going to be a very long presentation. Back to my example. So this is the partial sum of squares, and then you just need to divide this value by 2, by the degrees of freedom. For example, I'm going to do this. If I divide the 101.4 divided by 2, so it's going to be 50.7, which is 50.7 here. This is what STATA is doing for us. And then the F is Nedecore. This is the value, the actual value of the F test. But as I say, the value you should look at is this one and this one. I mean, you don't need to look at anything else. Just look at this value, the p-value, and adjust R squared. That's it. Okay. I'm just trying to explain to you the whole output, but you don't really need to do this. You don't really need to know about anything about this. I mean, it's useful to double check your output and to make sure that the STATA is doing the right things for you, but you don't really need to do this. So as I said, the value for the F is going to be this value divided for this value. So if I take this value, 50.7, and then if I divide this value for this one, and then I'm just going to display this. So it's going to be, according to my calculator, it's going to be 0.12439004. and state data is going to be 0.12. So state data is right. This is the calculation, yeah. And then according to this, you just need to go to internet, look at the F-Snedeker table, and look at the p-value for those degrees of freedom. And then you will see on the internet that the p-value is going to be something like this. Okay, and then the interpretation, obviously, if it's more than 0.05, so it's not significant. I'm not surprised because my model is very useless, and then my p-value is quite far away from the significance, so I'm not surprised about this. And then this is the same story for the within group variance, which is the residual variance, and the same story for the total variance. Any questions so far?
Yeah, I have a question, Wilson. Sorry for interrupt you. So I can conclude that when the add R square are a negative or have a negative result, is useless. Sorry.
It's totally useless. Totally, completely useless. I mean, if it's negative, I mean, there's nothing to do with your model.
Okay.
It should be always positive, and it should be always ideally more than, as I explained to you, more than 80%. But
Okay.
remember that you have to multiply this by 100 to convert this in percentage. And this is the percentage of explanation of your model. Okay?
Okay, okay,
So,
perfect.
Yeah, great. So I think I'm done with the one-way ANOVA. I'm hoping you have understand one-way ANOVA and the analysis of the covariance. And then my next topic is going to be the factorial ANOVA. So in order to do this, let's go back to the editor. I don't think I'm going to need this variable anymore, so I'm just going to.
Wilson, sorry
Yes.
to interrupt you. You did an output for Ancova before. Do you mind going back and explaining the output?
Okay, let me see. Actually, I can run the Ancova for you. So again, it's exactly the same interpretation. I think Daniela was the one who was speaking. So it's the same output, the same layout of the output, as you can see here. But you're just adding a new variable, which is age. And in this particular case, I mean, the interpretation is exactly the same. It's not going to be exactly the same because I'm adding a new variable, but the adjust R square interpretation is exactly the same, so it's completely useless. And this is going to be my my model, which is the between group variance, and then these ones are going to be my within group variances for group and for age, and this is going to be my within group variances. Within group variances. So sorry, this is the within group variances. The residual variance is always the within group variance, all right? This is the total variance, okay? And then this is the between group variance, which is the one I'm interested on, okay? So because we got two variables in my model, two independent variables in my model, so this is not going to be the same anymore like this. You can see here is the same number, but you can see here, no, it's not exactly the same, but I mean, what I'm trying to say is that this is going to be the between group variance, this one, the model, this is going to be the within group variance, and this is going to be the total variance. And these ones are the components or my between group variances.
So
group is the independent variable, and age, you're treating age as an independent variable as well. I thought
Yes,
it was a dependent.
Yes, you can see here the dependent variable first. So my dependent variable is sorry. It's saying here that my connection is unstable, but can you still hear me?
yes, we can.
Okay, yeah. So this is the dependent variable, and these are my independent variables: the variable group and the variable age in my Ancova. And don't forget the C. The C is very important because the C.
Okay, thank you.
With the C, you are saying to Anova, look, this is my continuous variable for my Ancova model. Okay.
Because in this situation, we treating age as group, another variable that will influence our outcome, right?
In this case, we are not. It's not a group, Karla, because this is a continuous variable. I'm not using this variable, which is the age categorical. I'm using the continuous age. But yeah, this. I mean, this explains my. Hopefully, these variables are the ones, which are going to explain my outcome, the creatinine clearance.
And for example, to understand if we found a statistically significant difference, we will evaluate model, right? And evaluate the p-value of the model.
Of the model, yes, which is this one.
And then to understand if age influence our outcome, we will evaluate the p-value of age. Correct or not?
The p-value of age, yes, correct, Karla, yes. Actually, I'm going to explain to you something that, I don't know if I should explain to you this. Let me just see. Before explaining to you this, yeah. Let me see here. So as you can see here, don't worry about the order of the independent variables. I mean, the syntaxis in STATA tells me that you have to type Anova and then the dependent variable and the independent variables, okay? So the dependent variable is always first. This is a rule, okay? But the order of the independent variables, it doesn't matter really, it doesn't matter. So as you can see here, I just type group CH and then CH group, and it's going to be exactly the same output, which is also important. So don't be confused about which one should be first from your independent variables. This is exactly the same output. The only difference is that the group appears here first and the age here second, and then the age here is first and the group is second. But as you can see here, the group is 45.38 and the group is 45.38. I think this is important to clarify this as well. I was going to show you something that I don't know if you can understand my slide. So this is a two-way Anova in order to clarify Karla's question. So just imagine, and again, this is a different example, but just imagine that you got two variables, and the two variables, obviously they are categorical, because if you are adding a continuous variable, this is not going to be two-way Anova anymore. So imagine that your factor A is going to be the, let me think first. Yeah, let's say that the factor A is going to be your group. So you got again a rivaroxaban, apixaban, edoxaban, warfarin, and placebo, for example. And then your factor B is going to be, for example, your categorical age. Okay, so for example, this group is going to be less than 40-year-old. This group is going to be between 40 and 60-year-old, and this is going to be more than 60-year-old. So I'm just trying to compare, to merge this model in just one model. So because my first variable has got 5 levels, this is what we call levels, the number of variables here. They are called levels, and because of my factor V has got 3 levels, so they've got 2 different levels. But the way STATA calculate this for me, I'm hoping this is not too complex, but this is the way. So as you can see here, my factor A was the group. So I've got 5 groups, but then STATA is going to analyze these 5 groups adjusted for my categorical age. Yeah. So in each group, there are 3 categorical age, because I said STATA to categorize my data set in 3 variables for age. So adjusted for the age, STATA is going to tell me whether or not this difference in the means are significantly different. Yeah. On the other hand, this is why there are 2 p-values here, because the STATA also is able to calculate for the age, for the variable age, which has got 3 3 levels. Again, less than 40, between 40 and 60, and more than 60. And then each subgroup, each level is going to be analyzed, adjusted for the group. And because there are 5 groups, so there should be 5 groups here, 5 groups here, and 5 groups here. I don't know if you can understand my point.
Wilson, one thing that I'd like to ask you to try to help us, it's regarding the name of the variables. I guess me and other students understood age as another dependent variable. But now you clarified us that the clearance of creatinine is the only one dependent variable, our outcome. And
this is very important. This is very important. Don't be confused with this, because the Ancova model only tolerates a continuous variable as an independent variable, not as a dependent variable. So the independent variables is included in the right side of your equation, as I say here. Yeah, I did explain to you here. I don't know, where is it? As you can see here, this is my dependent variable, and this is going to be independent, and this is going to be independent. Don't be confused with this. The continuous variables are always independent in my Ancova model.
Yes, and the test only allows one dependent variable, right? So we only can add one outcome, for example, in a test when we are trying to compare them. So I guess that's another way to remember that our outcome is our only one dependent variable, and the other ones are group, age, and other aspects that you want to evaluate are independent variable?
I don't have an answer for your question, Karla, but we can try. I mean, let's go for the error and let's make up some data here. All right. Anova. Dependent, and then independent, and then I'm going to add one here, which is the age, which is continuous, and my variable that I just made up is continuous. I'm going to state that this is continuous, and this is continuous, right?
Yes.
So we got an answer for your question, Karla. We can include more than one continuous variable, as you can see here. In my example,
we can.
Yes. So this is the dependent variable. This is the independent variable. This is my continuous variable because I say to state that this is continuous, and this is my continuous second continuous variable because I did state that this is continuous.
Flavia, this explanation answers your question?
Yes, Karla. Thank you. Thank you, Wilson.
Great.
And I guess, Wilson, this is great also to show to students when we add variables in our model, we increase the R squared value because, as you explained in the beginning, sometimes adding values and information in your data, the statistical tests understand that the model start
oversaturated.
Yeah, and sometimes we have a significant p-value, but completely insignificant clinically result.
Yes, exactly, Karla.
Also, sorry to interrupt you again, sure. But I didn't get the difference between Way Anova and Ancova, because in Ancova before you take age as a covariate. So we first need to adjust age according to the groups. I get that. But in the Way Anova, you add age, and I think you consider age as an independent variable and a continuous one, and which is also an assumption of Way Anova. So could you, I don't know, explain again, sorry for that, the difference between Way Anova and Ancova? Because I think that is a doubt that we are having as well.
Sure.
Sorry for that, really.
No, it's absolutely fine. So I was mentioning the, let's run again my comment here, and then again, this is going to my dependent variable, and then we are talking about Way Anova. So I need to add my group here, and then I'm going to add my second categorical variable, which is age cut, because I generate that one, and this is going to be a Way Anova. Why Way? Because I've got two independent variables, and the two of them are categorical, right? Group is categorical, and age cut is categorical. On the other hand, if you want to run the Ancova, so it would be exactly the same as this, but instead of age cut, I'm going to state that I need to include a continuous variable, and this is going to be continuous, and this is going to be my Ancova. The interpretation is very interesting, actually, because as you see here, the adjust R squared is exactly the same as here. You see? This is why it's all related. So it's exactly the same here and exactly the same here. And the F value is not exactly the same, but it's very, very similar, this one. But there is a big difference between the two-way ANOVA, and the difference is that I'm including a second independent variable as categorical, which is age cat. As you can see here, my age cat variable is definitely categorical, and my age variable is continuous. So I'm going to say here that age is continuous, and then ANOVA is going to understand that this is Ancova.
Okay, thank you so much, Wilson. Sorry for that.
No, it's all right. So guys, do you want to have a break maybe for 3 minutes, and then we can come back in 3 minutes?
Yes, but can I have a last question?
Sure.
When would you choose an Ancova, and when would you choose a two-way ANOVA?
Daniela, I guess it's related with your research question, as always. If you want to evaluate categorical independent variable, you go to a two-way ANOVA. So it always depends what makes sense for you to test in your population for your intervention. That's why the research question will guide us in everything, because in the end it's always, oh, I will test normality to know if I use this or that. I use linear regression for this secondary analysis. I will use Ancova or Anova for my primary outcome. So always depends on your research question.
Yes, and Daniela, as you can see here, there's not much difference among the outcomes. I wouldn't be surprised. As I say, they are just R squared is exactly the same. So, but I would say it's, in this case, it's not that relevant, but it is very relevant in regression models. So when you are building regression models, you will realize how different it is to include the continuous age as it is, or the continuous age as categorical. And the beta value is completely the same, sorry, completely different, and the interpretation of the beta value is going to be completely different. So remember, all this are completely related. So when you are building regression models, always remember that this is the same concept of ANOVA.
Thank you very much, you too.
I will, I'll be back in 3 minutes, okay? Thank you, everyone. Great, please.
One thing that Sobha just wrote on chat, and I guess it's really nice to conclude. Two-way ANOVA we will use with categorical independent variable. When we have Ancova, we use for one continuous independent variable and the other one categorical, the groups, the treatments, right?
Excellent. Yeah, that's the right interpretation.
Great job, Sobha.
Perfect. So I'm going to talk about Factorial Anova. Let me just see here. So Factorial Anova, let me just go back to my data here. I'm going to drop this variable because that's completely useless. So variable 6. Oh. Right, so I've just eliminated the variable 6, and then yes.
Wilson, are you sharing your screen?
I am. Can you see my screen?
I think I can see a node screen because I couldn't see the movements you made. Oh, now I see.
Yeah.
Sorry. So, yeah, great. So Factorial Anova. Factorial Anova, I just need to add a further categorical variable, and that's it. So let's go for my editor again, and then let's say, okay, let's say this. So I've just generated a new variable. As you can see, it's categorical. And back to my example, just imagine that we are running a multi-center trial, and then the hospital one is going to be one hospital. In this example, I'm going to use 4 hospitals. So I've just generated random numbers from 1 to 4, just to explain to you how to do this. So so this is going to be Factorial Anova. Let me just group. Yes, this is going to be Factorial Anova. Why? Because my dependent variable, sorry, just 1 second. Yeah, because my dependent variable is the creatinine clearance, and then I've got an independent variable, or which is the group, and then I've got an age categorical. I'm going to eliminate this because otherwise it's going to cause confusion. So I'm going to eliminate the variable age. I don't need this anymore. So you can see here, this is my dependent variable. It's a continuous one. And then I've got one categorical variable, which is the group. You see here, we've got 3 groups, as always, in my example. And then I've got a second independent variable, categorical one, which is age categorical. And then this is a 2-way ANOVA. And then you add a further categorical variable, which in this case is hospital. So this is categorical independent variable. There are 4 hospitals. So you can see here, hospital. Then if you've got more than 2 independent categorical variables, we are talking about Factorial Anova. That's it. So I'm going to run my Factorial Anova again, dependent variable, and then independent variable is going to be my group, my age categorical, and my hospital. Remember that the order of the independent variables doesn't really matter. And then you've got Factorial Anova here. And the explanation and the interpretation is exactly the same. But you see in terms of my diagrams, it's slightly more complicated because this is a different example, of course, but if you got 3 variables here, my first variable has got 4 levels, my second variable has got 3 levels, and my third variable is going to be three levels as well. So let's imagine that the factor A is the treatment. So we've got 4 treatments again. Apixaban, edoxaban, rivaroxaban, and warfarin. And my factor B is going to be my age, so less than 40, between 40 and 60, and more than 60. And my factor C is going to be the hospital in this case. So there are going to be 3 hospitals, so hospital 1, hospital 2, and hospital 3. So what ANOVA does for us, and this is going to be slightly more complex, but this is what ANOVA does. So there is a grand mean between the whole sample size. I've got a first factor, which is the group. So we got four groups, and the groups, the variables are called levels. We've got a second factor, which is called the age. So we've got less than 40, between 40 and 60, and more than 60, and so on. And for each level, ANOVA is going to generate, this is like a stratified randomization, really. It's going to generate 3 levels based on the allocation of the hospital. So this is the hospital 1, hospital 2, and hospital 3. And the interpretation is exactly the same, because whatever the p value is for ANOVA is going to be adjusted for the other factors. And this is the beauty of ANOVA. All right. So this is Factorial Anova. And then
Wilson,
yeah.
could you just show the values in this output? For example, so our p-value of our model, of our Factorial Anova would be 0.97, right? Not significant value, model.
Not significant for your model. You see here, you are always interested in your model.
Okay,
yeah? Great. Model. Okay, don't look at the within group variance, don't look at the total variance. Actually, ANOVA is not reporting any p-values for because it hasn't got any relevance. Again, this is the within group variance, this is the total variance, and this is going to be the between group variance, adjusted for hospital, adjusted for group, and adjusted for the categorical age.
Okay, and in the case that that we don't have this, the p-value is not significant, we just should not look for the group, age, categorical, and hospital p-values.
Exactly, and it doesn't make sense to make any post hoc analysis, because we already know that there's no difference between groups.
But if we had a statistically significant p-value, these other values, the p-value of group, age, and hospital, would matter for us, or we must go for a post hoc analysis?
I think what I would do, just go straight for the p-value, go straight for the p-value here, and then go for the post hoc analysis. I mean, if there's a difference, so you need to wonder yourself if the differences between which groups, between which categorical age, or within which hospital there is a difference. But this is going to be more complex, actually, because you got three independent categorical variables, and you have to look at every single combination.
Okay, thank you, Wilson.
So I think that's all I need to talk about Factorial Anova. If I have time, I would like to talk to you a little bit. Don't know what to do, really, because maybe we don't have time. Let's try this to see what happens.
Hi, Wilson. Christina asked on chat if make any difference the order of independent variables on Factorial Anova, or as Ancova, it doesn't really matter.
Doesn't matter. Doesn't matter.
Okay, thank you.
Sure.
There are 4 instead of 3.
Thank you. Right, sorry for the wait. So this is going to be exactly the same example. As you can see here, there are, well, it's not the same example because it's going to be repeat measures ANOVA. And so we got 10 patients, and then just imagine that we are now measuring for each patient three measures of the creatinine clearance. So for the first patient, for example, the first measure was 23, the second measure for the same patient was 34, and the third patient was 23. This is just an example, and so on for every single patient, right? So as I explained to you before, this is a wide format, but STATA is not going to understand your wide format, so you just need to convert your wide format to the long format. So you just need to type here. I explained to you, this is not really straightforward, but this is what you have to do in ANOVA. So you see here that immediately STATA is going to transform your data to a long format. So you can see here, it's exactly the same data set, but presented in a long format in another way. So for the first patient, you got 3 measures. I just call this variable time, and then for the first measure, 23, 34, 23, and so on for the second patient, for the third patient, until the 10th patient. The syntax is not really straightforward, but if you want to run repeat measures ANOVA, this is what you want, what you need to do. In order to do repeat measures ANOVA, you just need to type ANOVA. And then again, always the dependent variable. So my dependent variable is here. And then I say after the dependent variable, it would be the independent variable. But this is one of the exceptions because in between, I'm going to type here. This is the dependent, and the independent is going to be this one. Okay, but in between the dependent variable and the independent, why the time is independent? Because I'm just trying to, this is a variable I just generate here. So for the time 1, time 2, and time 3. So the time now is going to become my independent variable. This is my independent variable, right? And then in between the dependent variable and the time variable, you need to indicate its data what is going to be the variable that is going to be included within each patient, the three variables. So I just decided to call this a variable patient, but you can call it whatever you want. So hopefully, let me just see here. So yeah, so this is the repeat measures ANOVA. Again, exactly the same interpretation, but obviously the interpretation of the p-value, the interpretation. So you see here the adjust R square is slightly better than my other models, 36%, and the interpretation of the p-value is just the answer to my question whether or not this first measure is different from this one or from this one, or if the first measures are different from the second ones or the third ones. This is my question, my research question in repeat measures ANOVA. And then I'm not going to go in depth with the
because in this case, Wilson, our null hypothesis is that the measure will have not difference.
Yes, exactly.
So we reject the null hypothesis in this situation, showing statistically that there is a difference. So, but we'll have a next question to answer correctly, but this test answers this first question.
Yes, exactly. Yes, that's the right interpretation of my repeat measures ANOVA. This is the right interpretation. And I wouldn't really be surprised with the p-value statistical significance, because if you look at 56, it's quite different from 89, for example. Or if you look at this patient, 23 is quite different from 34. Or if you look at the second patient, well, second patient was 45. But for example, for this one, 67 is quite different from 43, and that's why it's significant. You see, it's quite interesting. And then I think I'm done with the ANOVA. And then
Wilson.
Yes.
Does it matter if one value goes up and the other values go down?
It doesn't matter, because ANOVA, remember, the ANOVA is going to tell you whether or not they are different. But ANOVA is not going to tell you, well, this is the first value is different from the second is different from the third, or the first is different from the third. In order to do that, you need to run a post hoc analysis.
So if I have a mix of patients that have the clearances increasing and others having the clearances decreasing, I will have significant results, even though, right?
You will have significant results because that's not your research question. This research question is it requires another test, a statistical test for ordinal variables, not for categorical.
Okay, thank you.
All right.
Renata, Renata asked how we interpreted this, because in your data set, some patients had difference and other patients had no difference. Renata, with this statistical test, we are proving that there is a difference, but we are not showing the size of the difference, or as Wilson said, the direction of the difference. We're just proving mathematically that patients, the values, the means of the measures are different, but we will, it's necessary in our interpretation of our data, it's necessary to run other tests to understand what the end of our question.
I believe so. I think so, but unfortunately, my knowledge regarding repeat measures ANOVA is not that advanced to reply to your question. And something that just came up to my mind, I don't know if I'm right, but the variable time is something that worries me, because this is what actually I'm trying to evaluate here, where or not the first one is different from the third, or the difference is the first is different from the second, of the second is different from the third. So actually, I'm not really sure, and sorry about this, but I'm not really sure if for this particular case of repeat measures ANOVA, we should look at the time instead of the model. I don't have an answer for this. I will need to have a look later on, but this is something that just came to my mind, that because I'm just trying to compare the times here, the one, the second, and the third. So maybe, I'm not 100% sure, but maybe we should look at this p-value instead. This is something that I don't really know, to be honest with you.
But maybe, Wilson, the post hoc analysis will help us also. Yes. Not only this, because the model works. The p-value of patient is significant, but as you said, time is not statistically significant. But yeah. I guess maybe a post hoc analysis will help us to identify what generate the difference, because that there is a difference we know with the model, but as you said, I'm not sure if time was the main factor that influenced.
Value to look at for repeat measures ANOVA, which might make sense, but I'm not 100% sure about this, about the interpretation of this model. I don't know. For the other models, yes, you should look at your model, but for this particular model, I think you should look at this value, but sorry, I don't really know. I don't really know. Sorry about this. Right, so I've got a couple of topics more, and then I will need you to tell me whether we should stop here, or there are two topics more which are important as well, which are non-parametric tests that are basically Kruskal-Wallis and Freeman tests. And the other one is the post hoc analysis. I don't think I will have time to discuss with you both of them. So we could either stop here and finish the presentation because it's been 2.5 hours now, or I can explain to you a little bit the non-parametric tests, or I can explain to you a little bit the post hoc analysis.
Wilson, I guess it was a wonderful presentation. I agree that it's a bit long, but there is no other way to explain a lot of things that you explained us. So it's up to the students, if students want to keep. Probably I will have more 30 minutes, then I will have to go lunch with my husband, but if the students want to continue, it's okay. I can keep record.
All right. So I mean, I don't really mind, provided that you are not asleep. I can speak for 20 minutes more, and then we will finish the presentation.
Wonderful.
Great. So I'm going to talk to you about, I don't know what to talk to you about. I'm going to talk to you about the non-parametrical tests, which are Kruskal-Wallis and Friedman test. So Kruskal-Wallis is the equivalent for the standard ANOVA, the one-way ANOVA. And Friedman test is the non-parametric version for repeat measures ANOVA, right? So this is my understanding of the Kruskal-Wallis test. This is called the H test. And so again, we are just based in the ranks, and then the only difference with the Wilcoxon test that I explained to you the other day is that we've got three groups instead of 2 groups. So as you can see here, I've got 3 groups here. So group A, group B, and group C. I've got 2, 4, and 6 patients in the group A. I've got 7 patients, it's 3, 6, and 8 patients in the group B and 7 patients in the group C. And then I've got 21 participants here, each one allocated to each group. And then I've got a VAS score. This is a completely different example. In this case, it's not actually a VAS score because the value goes up to 20. But anyway, this is a continuous variable. And the continuous variable is organized in ascending order. So you can see here that the minimum value for my sample was 6, and the maximum value for my sample was 20. So once you arrange your data in ascending order, you just need to assign the ranks as for any non-parametrical tests. So this is the ranks and this is the ties. I did explain to you the other day, but I'm going to explain to you again. Because this value is 7 and 7, so the rank is not 3 anymore or 4 anymore. This is going to be 3.5 and 3.5, which is the average of 3 plus 4 over 2. And same for any other examples here. So you've got the ties here, and this, based on these ties, you should be able to sum the ranks based on this equation, and then you will come up with a number here. Let me see, what was the number? Yeah, 6.17. And based on this number, you just need to go for a chi-square table on internet and see whether or not this variable is significant. In this case, because 6.17 is greater than 5.99, which is the critical value for my degrees of freedom, for k minus 1 degrees of freedom. So I'm going to reject my null hypothesis. I'm going to say that there is actually some difference between groups or among groups. This is the Kruskal-Wallis test. And in STATA, you just need to, I'm going to clear this. And I'm going to go for the data editor. Oh, no, sorry. And then the syntaxes for Kruskal-Wallis, sorry, I need to rename this. So the syntaxis is actually the same as the t-test. So you just need to type K-Wallis. So dependent variable here, comma, and by the independent variable, which is group. And then you're going to have here your chi-square for the critical Wallis. And then, as you can see here, the chi-square with the ties is going to be 0.14. So it's not significant, the test, which means that there is not proof that there are differences among groups, among my groups here. And this is all you need to do for the critical Wallis test.
Wilson, Gisela is asking why it's necessary to use rank in critical Wallis. Gisela, it's because we have non-normally distributed data. In order to be able to evaluate, we can't use the test and other tests that normality is an assumption. So you should use non-parametric tests. And as Wilcoxon sum and Wilcoxon sign tests, they use ranks. They transform our data, continuous data, in ranks. So this test is able to deal with rank. So that's the why STATA will do it for you, but Wilson showed it very well how it works. STATA will interpret the continuous variable and will rank then organize it.
Sure. Yes, that's true, actually. So you have to keep in mind that many of the non-parametric tests are based on the rank. So we've discussed this in our office hours as well. Manui, Ney, Wilcoxon, critical Wallis, Friedman, Spearman, all these tests are based on the ranks rather than the actual value. And this is the reason, if you understand this is the reason why we usually say that the non-parametric tests are not, have not statistical power, because we've lost lots of information here because we are replacing the actual numbers, the actual values by the rank, which is necessary for run the test, because all these tests are based on the rank, but certainly is not good for the statistical power. So that's why in general, non-parametric tests have less statistical power than the parametric ones.
Sophia also asked Wilson, the value of 5.99 is a kind of that numbers that is in the table that we use to find the p-value. Is it correct? This is the value for Kruskal-Wallis test?
It is. So this is for my example, because I've got three groups. So 3 minus 1 is 2, and the degrees of freedom for the critical value for the degrees of freedom of 2 is going to be always in the chi-square distribution. I'm talking about the chi-square distribution. It's going to be 5.99. It's easy to look up the internet. Let me see if I can for you. Chi-square.
Sorry for interrupting you, Wilson.
Yes.
This table where we get this value of 5.99, it is a standard table that we don't calculate, right?
No, we don't. This is the original.
It is a general table, or is it different for different cases?
It is a general table. So you can use for every cases. And this is what Ronald Fisher did for us in 1960s, I think. So this table it actually works for everything, provided that you are using that test, obviously, because unfortunately you've got a different table, theoretical. These are theoretical tables, assuming that there is no difference in your data. So that's why you have to compare with your actual value. Let me see if I
and
can.
I guess that's the why one of the main assumptions that our study population comes from a random sampling also, right?
Yes,
So
exactly.
that's the main assumption, and that's the why sometimes we say, oh, it's not really random, and maybe it's a limitation of my study, because all statistical tests, they assumes that our population is it really represent a random sample of the whole population.
True. Yes, exactly, Karla.
And the H value is a chi-square value, right?
It's not the chi-square. It's not exactly the chi-square value, but it's based on the chi-square distribution, which is different.
Perfect. Thank you, Wilson.
And in my see degrees of freedom here too, and you just need to go here, 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 and then this is your significance. This is your significance, and then you can see here. Can you see this here? 5.99.
Yes, we can.
Yes. So this is why I'm using the 5.99 here, because 6.17 is greater than 5.99. So I'm going to reject my null hypothesis. Okay. And then finally, the Friedman test, which is the equivalent to the repeat measure Anova. So again, this is a different example because you have to have more than 2 measurements for every single patient. So you've got 12 patients in my example, and then you got here the measurements. In this case, they are VAS scores. They are trying to quantify the level of pain of the patients. In my particular example, for example, this patient had a lot of pain here, and then after the intervention, the pain reduced a little bit, and then the pain came down to 7 on the third measure. So my question is if this is significant, this change. Okay, that's why I'm using the Friedman test. So again, rank again, and then you just need to rank these values. For example, here the less value is 4, so that's why the rank is 1, and then the next value is this one, so that's why the rank is 2, and so on. Yeah. Whenever you have ties, for example, here you have a tie here because you got the same value 5 and 5. So you just need to, this is the less value, so it's going to be 1. And then this is not going to be 2, but the average between 2 and 3, so 2 plus 3 over 2, which equal 2.5. And then you just need to, once you calculate this, just need to calculate the sum of the ranks here. So this is the sum, the summatory of the ranks here. And they just need to square your ranks here. So 3 squared is 9, for example, or 2.5 squared is equals 6.25, for example. And based on this, so you got the equation here. I'm not going to explain to you this, but well, my point is that the Q test in this case is going to be 15.06. And then again, the Q test is approximately distributed to the chi-square distribution for K minus 2 degrees of freedom. Again, because I've got 3 groups here, 3 measurements here. So the degrees of the critical value is going to be again 5.99, and because 15.06 is greater than 5.99, so it's going to be significant, and I'm going to reject my null hypothesis. And as you can see here, 15.0698 is exactly this value here in my STATA, 15.0698. And I think that concludes my presentation for today. I think we had a nice discussion regarding all the versions of the ANOVA, all the parametric tests we can use. I really appreciate your time because I know it's very difficult to combine the clinical duties with your PPCR course, but I think you are doing amazing. And you know, because going to the office hours on Wednesdays, and then live lectures on Thursday, and then optional lectures on Fridays, and again office hours on Saturdays, and again here so on Sundays. So I really appreciate your time. Thank you very much, everyone, for joining us. As always, please don't hesitate to ask questions if you have. I'm very happy to help you. I know it's very difficult. This is a very intensive course, but I can see your progress, which is very reassuring for us as TAs. I'm happy to take any questions if you have. Otherwise, we can conclude the presentation.
Wilson, I have to thank you so much. It's incredible. Your patience, your way to teach, it's really great. Thank you so much. Thank you for your time. I imagine that anesthesiologists in London in this time is a little bit challenging. I hope you are safe and healthy. And we are really happy to have you as our teacher today. So thank you so much. I have no words to thank you.
Great. Thank you, everyone. Thank you so much. And so yeah, I think we had enough statistics for today.
Yeah, I will stop the presentation.